and welcome to this lecture. So, we have seen how to find adjoint given the operator and how the operator is defined in terms of a matrix or something. So, now we are going to see a few basic operations that you can do with the adjoint. Okay. So, for instance, we've seen that you can add operators, right? You can do a S plus T. If you have two operators S and T, you can add two operators. What happens if you take adjoint after adding the two operators? Okay. So, this adjoint, taking an adjoint is like an operation on a matrix, right? You have a matrix or an operator, you take adjoint, it becomes some other operator. So, you can now see how this adjoint will play with addition, multiplication and all of that. So, you have to think of adjoint also as a very useful operation that you might want to do on an operator or matrix to get other interesting operators. So, here is a way in which it interplays with sum. So, if you have two operators S and T, you do S plus T and then you take adjoint. It is the same as taking adjoint for S and T separately and adding. Okay. So, it is very easy to prove. So, the way you prove these things is actually very easy, right. So, you look at this, I want to do adjoint for S and T, okay. So, I will look at the very basic definition of my adjoint, right. So, what do I want? I will look at S plus T dot, S plus T acting on V dot U, right. I have to eventually write it as V dot something, okay. So, now this I know by just basic linearity is the same as SV dot U plus TV dot U, okay. And now you use your adjoint here. So, this I know is the same as V dot S star U plus V dot T star U, and then you use the linearity on the second argument, right. So, you know that the second argument also it is going to be the same. So, this is going to be V dot S star U plus T star U, okay, and that is the same as V dot S star plus T star U, okay. So, I hope this is clean enough. You get the second operator here, and then that S star is the adjoint of S itself, T star is the adjoint of T itself, and then when you add, you can add these two together like this, okay. So, I guess, so see, remember, with respect to addition, the second operator also just adds. Only when you multiply a scalar, you get those other things. So, here I am just adding. So, this will be working out correctly. So, from here you can identify that from this structure you can identify that S star plus S plus T whole star is the same as S star plus T star, okay. So, this is the sort of method that one uses to prove these kind of results. Now, once you have the result for the operator, the analogous result for the matrix is very clear. So, if S is represented by A and T is represented by B, so A plus B Hermitian is A Hermitian plus B Hermitian. This operation is also very, very clear, isn't it? A plus B Hermitian. Hermitian is basically taking transpose and conjugating. It does not matter whether you add first or you take individually the Hermitian and add, you should get the same answer, right. So, you see that very easily. So, here is scalar multiplication where the conjugate of A will make an appearance. So, I am going to take T and multiply with A and then take adjoint. When I do that, it is the same as A bar, the conjugate of A multiplying T star. So, notice this how a constant gets, when you multiply by a scalar, you get the conjugate of that. That is because of the nature of this operation of T star, okay. So, the analogous matrix thing is A times A whole Hermitian is A bar times A Hermitian. You can prove these things very easily. Once again, you can go back and look at the proof that I made for this plus, modify it suitably, and you will get this answer, okay. So, it will go to the other side and then you will get a bar, okay. Hope this is reasonable. Should we try a proof here? So, we can try a proof here also if you think that can be done, if you are interested in such stuff. So, you are looking at AT whole star, that is the same as ATV dot U. So, that first you have to send the A to the other side. So, when you send the A to the other side, it becomes the same as TV, or maybe you can keep the A here on this side and send the t alone to the other side, right? So, but maybe that's not very useful. So we will keep the t to this side, send the a alone to the other side, and that will become a bar, right? So, because if you send a to this side, it is same as a bar multiplication, only then you will get the correct thing. Okay, so now you use your adjoint property, tv dot anything is v dot t star times that. So, that is the same as a bar t star u, and that becomes the adjoint. Okay, so these are easy results to prove, but it's good to get some practice if you're interested in such stuff, how to do this proof. Now, product is something that is slightly more interesting, product or composition. Okay, so addition of two matrices is easy, multiplication of a matrix by a scalar is easy. When I multiply two matrices, what happens? If I do composition of S and T and then take adjoint, here is an interesting little twist. You get T star composed with S star. The order reverses. Okay, same thing happens with the matrix here. AB whole Hermitian is B Hermitian times A Hermitian. Okay, so this is one thing where the result is a little bit different. So let me write down the proof here for this for you. So why is that true? So we know that SV dot U is V dot S star U, TV dot U is V dot T star U. This we know already. Okay. Now what do I do for S of TV dot U? So this is S composed with T. Okay, right? This part is S composed with T, acting on V, and then I am doing a dot with U. Okay. So now this, right, so this you treat this TV as like this V here. Okay. So this, instead of V here, you look at this TV here and then use this relationship. So you get TV dot S star U. Okay. So we have taken this relationship and instead of V I have put TV. Okay. So if you put TV here, you get this guy, right. So TV dot S star U. So now what will I do? I will look at this relationship and instead of U, I will put T star S star U. Okay. So then what will happen? I will get V dot T star of S star U. Okay. So hopefully you see this, and that is clearly proof that, you know, S composed with T V dot U is V dot T star composed with S star U. So it happens in the other way around. Okay. So this reversal happens in the composition or the matrix multiplication. Keep this rule in mind, it's a little bit important. Here's an example on how these kind of things are used. Supposing you have A plus I times BC whole Hermitian. This is going to be A Hermitian. Notice how this plus I became minus I because they have to conjugate, and then BC became C Hermitian, B Hermitian. Okay, so this is the way in which these kind of results are used when you deal with adjoints. Okay. Now here is a interesting and simple operator called the identity operator. Okay. So if you take the identity operator, IV equal to V for all V, the adjoint is I star is I itself, right. So if you have an adjoint for the I star, right, so I is just identity, it does not change anything. So the I star will also be I. You can write down this functional we have here, IV dot U is V dot IU is V dot U, it is the same. So I star has to be equal to I. And even if you think in terms of the matrix, I2 is the identity matrix, 1 1 on the diagonal, you do Hermitian on it, you get the same thing again. Okay, so I2 Hermitian is I2, right. So that's an interesting and important thing to note. So one question you may ask is, what are all the matrices which will give you, will be equal to its adjoint, right. So these kind of questions you may ask, that we'll see in a subsequent lecture. Okay, so these kind of questions are very interesting. Identity is not the only thing, there are others also, they have some powerful properties. We'll study that later. Okay. Here's an example of how identity will enter some adjoint type manipulation. You may have to do a manipulation like this. Typically, when you think of eigenvalues and all, you may have to do manipulation like this. T plus AI whole adjoint is the same as T adjoint T star plus A bar I itself. You don't need to do I star, right? I star is the same as I. So you get this kind of examples here. Okay. So this is the identity operator. And finally, in this functional I've been talking about, you can interpret it completely as a matrix identity. Okay, so I'll show you how it's done. Linear operator T represented by this matrix. The functional that we've been looking at when we defined adjoint is this TV dot U, right, which we saw as the same as V dot T star U. This f of V is a scalar, as we know. So you can have a very matrix algebraic interpretation of this guy. Okay, so how do we do that? First of all, you recall that V dot U is U Hermitian V, right. This is the matrix multiplication. I put an equality here, so clearly it's it's all both are scalars. So V dot U is U Hermitian V. Okay, so in terms of matrices, what is f of V? F of V, if you take this definition, right, it's U Hermitian times TV. right? But TV is m of t into v. Now here I have a scalar again, so this is the same as f of v, right? So I put a colon here, it's actually be equal to, so f of v is equal to this u Hermitian m of tv, okay? So that is the matrix representation of this dot product, okay? So now this thing can be rewritten as follows, right? So I know u Hermitian m of t, I can rewrite it in this fashion, okay? So this is the clever way in which I am rewriting this. I am writing it as m of t Hermitian u, the whole thing Hermitian acting on v, okay? So notice how this has been changed a little bit. So this has become m of t Hermitian. See, I want v dot something, right? So I only want v here, everything else here should be a Hermitian. So but this m of t alone is not Hermitian. So I'll write it like this. I will put it as m of t Hermitian u whole Hermitian. Notice how the order got changed here, okay? Right? So the order got changed. So if you want to expand this out and write, u Hermitian is u1 bar, u2 bar in a row vector. M of t is as it is, v is a column vector v1, v2, so that this becomes a scalar, right? This row vector times a 2 by 2 matrix times a column vector is a scalar quantity, okay? So this is the same as this m of t Hermitian, which is this ACBD, the conjugated, times u1, u2, the whole Hermitian times v1, v2. So these two are exactly the same, okay? These two are exactly the same, and that's the identity that gives you the t star to be m of t Hermitian, okay? So I hope you see that. Okay. So this is a matrix theoretic view. I just wanted to give it to you to tell you that, you know, you can just think of everything in terms of matrices if you want to. Okay. So that concludes like sort of operations you may do with adjoint and how you need some comfort with the algebra that you have to do with adjoints, adding, multiplying, after taking adjoint, after that what happens. All of that is very important in what we're going to see next. Thank you very much.